I would like to welcome you to our today's topic webinar, CrysAlis Pro Simulator for Crystallography Teaching, which is held now at 10 a.m. and also again this afternoon at 4 p.m. Central European Time. Our today's presenter is Dr. Christian Schürmann. He is application scientist for single crystal and powder X-ray diffraction. He will demonstrate one of the lesser known features of CrysAlis Pro, namely the simulation of single crystal diffraction data. This feature will be used for diffractometer testing and teaching purposes without using physical presence at the instrument. Christian, here you go.
Thank you so much. So I'm going to quickly turn off my camera. Let's go. So this webinar is being recorded and uploaded to YouTube. You will receive an email with corresponding link and in the aftermath of this webinar. Please check out our past webinars on our webpage and the YouTube channel. If at any point during the webinar you have a question, please feel free to submit it by clicking the Q&A button on the bottom of your Zoom screen. My co-host will collect all questions and we will answer them by the end of the webinar. Before we start, I would like to ask all of our users to join the Rigaku X-ray forum. Here you can get updates on Rigaku activities, the latest version of CrysAlis Pro, and interesting discussions on all fields of crystallography. If you are already a member of the forum, I would like to encourage you to subscribe to your specific fields of interest so you get email alerts when something new comes up. The CrysAlis Pro simulator is a powerful tool, and using it wrongly can lead to some very serious issues. We therefore have to start with a couple of warnings and disclaimers. Never ever use your instrument control PC for running the simulator. The setup of the simulator will override your system's configuration files. This includes the collision model, so apart from software issues, this can lead to collisions. Performing the simulator on your instrument control PC can seriously damage your system, so please just don't. The CrysAlis Pro simulator is also a powerful tool when it comes to the simulation of diffraction data. It can simulate seemingly valid data from any structure model. Any structure model means that these include made-up ones. While this might be justified in the context of teaching, the publication of fake crystal structures is more or less the worst thing you can do as a crystallographer. So please don't do it. First of all, because cheating is bad. Second of all, it will come up. We are in close collaboration with the Cambridge Structural Database, and they will detect if you try to upload fake data. And even if you manage to fake data in a way that you think it will not be detected, don't do it, because it discredits you, all of us crystallographers, and ultimately the scientific method itself. And especially in difficult times like these, it is more important than ever to uphold to the highest standards of science based on trustworthy data. The third and last warning I would like to give is to never assess the physical hardware based on the simulation. The simulation and reality differ quite a bit. The simulated intensities are independent from the simulated radiation source. You won't see a difference between a sealed tube or a rotating anode. And please keep in mind that in reality, our rotating anodes have at least an 8-fold higher intensity than any microfocus sealed tube currently on the market. The simulated reflection features like spot size and smearing are also implemented in the independent from hardware features like the incident beam divergence or the detector's point spread function. You basically will not be able to observe a difference between a scintillation and a direct photon counting hybrid pixel detector, while in reality, the latter one provides way superior data quality. The simulation's performance heavily depends on your processing power. In some cases, the actual data collection would be faster than your simulation. The default collision model used in the simulator is very conservative, and therefore the possibilities of an actual properly calibrated system exceed the simulated ones. If you are interested in purchasing a single crystal diffractometer, please contact us and we will show you the real system and collect real data with you. So after we are done with the warnings and remarks, we come to the actual use of the simulator. First of all, let's talk about why and when to employ this CrysAlis Pro simulator. You can simulate any Rigaku diffractometer. The simulator was designed for debugging purposes exclusively, and everyone can employ the simulator to test the software and when it comes to the observation and reporting of bugs. Using the simulator, you can easily teach the basics of diffractometer usage, the CrysAlis Pro workflow, and the design of specific experiments without occupying your diffractometer. You can test different hardware setups. If you ever wondered how it feels to have a system with a huge Eiger 4M detector, just simulate it. But please keep in mind what I said about assessing the instrument based on the simulator. With any simulated instrument, you can also collect simulated data. You can process them and perform a full structure determination. These data can be used for teaching and testing. You can simulate data with clear-cut problems like predefined twinning and train the processing of such data. Furthermore, you can simulate data from a fake structure. So in order to test students, maybe without worrying about them finding the published one. I stated that any Rigaku single crystal instrument can be simulated. That's true for almost all instruments of the last 10 to 15 years. Simulating the current generation of instruments of the XtraLab Synergy series with Hypix, Pilatus, or Eiger type detectors is very easy. You won't need additional files. For simulating the older instruments, you will need additional configuration files. If you want to simulate your home system, you can simply copy the required files. That's easy. Older Oxford diffraction or Agilent Technologies instruments require detector correction files if they use older CCD type detectors. If you want to simulate that kind of instrument, a good place to ask for the required files would be the Rigaku X-ray forum. To simulate old Rigaku type instrument, and the XtraLab Mini requires the configuration of the MSC server. With good reasoning, we can help you with that. For now, we stick to a simple example and simulate the Rigaku XtraLab Synergy S dual-flex with a Hypix 6000 detector, which is currently one of our most popular instruments. Therefore, let me switch the screen. You see my cursor position is highlighted by a red dot, and you will be able to follow the next steps by this panel on the left-hand side. First, you have to start CrysAlis Pro for PAR file generation. You might have never used this tool before, but you can find it in the Excalibur folder of your Start menu or the Service folder of your Excalibur installation. I have it linked to my screen here. Once you started it, this menu will pop up and ask you what kind of instrument the PAR file should be created for. Today, we want to simulate a Synergy S system. Therefore, I select the first option. I press OK, and a new window opens. The first option asks to browse for a machine folder. As we want to build the simulation from scratch, we do not do this. Instead, we keep the default folder and continue with next step. Now we have to choose a platform. We want to simulate a Synergy S dual-flex. Therefore, I choose this instrument from this drop-down menu. In the most popular configuration, the home source is a copper photon jet, and the offset source is a molybdenum photon jet, which I choose from the corresponding drop-down menus. And as camera type, we keep the Hypix camera, but in principle, there are other options, as you can see. And we continue with next step. In this step, the required files for PAR file generation have to be located. For our simulation, we can ignore the goniometer correction file, GON, and create a new CCD file for the Hypix camera. And we choose as Hypix type 6645, which corresponds to the Hypix HE version, 6000 HE version. For the simulation of older CCD type detectors, you will need to apply additional files in this step, which you can copy from your system or befriended crystallographers. Here, we can choose different experiment parameter. We can choose to activate the option to run the instrument in dual mode for high pressure cells or a plate screener. We can choose whether the program starts in small molecule or protein mode, and we can choose the starting wavelength. Here we keep everything to the default values and simply continue to the next step. In this step, we configure the video settings. Interestingly, you can use any video input as your crystal camera. As we will run this without a physical instrument, we will obviously have no real crystal camera accessible. Connecting this to your webcam is funny, but I will use this virtual OBS camera instead. Next, we can load an instrument parameter file for instrument corrections. Here again, we stick to the default and continue to the last step. Here we can choose a file name for this PAR file, and most importantly, flag it as a simulator. We press OK, and a warning pops up that we acknowledge. Finally, we have to choose the crystal mount in use, as these affect the collision model. And with that, we successfully configured our virtual instrument and are good to go. We now start the online version of CrysAlis Pro. So CrysAlis Pro starts as if the instrument was connected. At the startup, the goniometer is initialized, and we can start a new experiment once the instrument is initialized by pressing the Start Stop button and select Start New. Usually, we would now continue with the mounting of the sample. This is not necessary in the simulator, and therefore we start with screening the sample. Please observe that now the copper source is ramping up. The tube operation is included in the simulator, and we can easily switch between copper and molybdenum source by clicking the corresponding button up here. Most of the functions of the basic system are accessible in the simulator. Not included are, for instance, the temperature control device, as this would require an external instrument, or the beam divergence control. The frames are recorded like in any other experiment. However, the frame collection time is sped up a bit. So after screening, we perform a what is this experiment. We start the experiment by clicking this what is this button and key in some elements that are suspected to be present, and continue with start. For more detailed information on the screening and data collection features of CrysAlis Pro, you should see the webinar by Pierre Magores on sample screening. In default mode operation, AutoCam is automatically activated in the simulator, even without license. If you want to have if you do not have an AutoCAM license and ever wondered how this feature of CrysAlis Pro works for you, you can experience it in the CrysAlis Pro simulator. While the data collection is starting, we can check the preliminary cell here. And there are already a couple of entries in my database. The automatic data processing routine already started. And of course, the data processing is fully included within the simulator. And AutoCAM already started and tried to solve the structure. And after some seconds, we were able to see the structure of ULIT, because ULIT is the default structure for the simulator, at least for small molecular mode. If you run the simulator in protein mode, the structure is 1DTX, and this then is the default structure. Of course, we now could proceed by refining the structure or by collecting a full data set, but this might be boring. I would rather like to show you how to customize the simulator. So in order to access the simulator options, you must open the CrysAlis Pro command shell by clicking the CMD button on the left-hand side. Then you type in the command XX theme setup. And press enter. The simulator setup window opens. Here you have a number of options to customize the simulator. We start on the top left-hand side with the customization of the sample. By pressing Load ins res, you can import any crystal structure. I go to this folder and import this made-up structure, which I called fake structure. It is depicted on the left-hand side, and it chemically makes no sense. You can also change the cell by selecting Edit Cell. The mosaicity given here is not directly giving the actual crystal mosaicity, but more empirical values for the reflections spread function. As this has been implemented in the times of scintillation detectors, the spreading seems to be too strong compared to actual data with a state-of-the-art directly photon counting hybrid pixel detector. In order to create more realistic data, I set the mosaicity to 0.5 degrees. However, if you want to simulate problematic data, you can set the mosaicity to a very high value and create overlapping reflections. You can choose to input a custom sample orientation, or you can just click random orient in order to randomize it. You can choose to change the sample orientation at each start of the data collection by checking this box. The diffraction power is one value to scale the reflection intensity. If you use a custom structure, you might have to adjust this value. In the case of my fake structure, I made good experience with a factor of 100. So next, we are going to talk about the adjustment of the simulated instrument. The frames are not collected with the actual collection time, but the time it needs to compute them. So this depends on the processing power of your PC and the detector size in some instances. Additionally, a frame delay can be applied. I unselected because we want results as quickly as possible. You can also simulate the goniometer movement time. We stick to the speed factor of 0 that lets us ignore the goniometer movement. It is possible to ignore the beam stop area and simulate data in that area by checking this box. And there are possibilities for the application of a range of hardware connectors that I do not any reason to use except for debugging purposes. If you like, you can even simulate to have copper and molybdenum beta radiation mirror optics. You can also simulate high pressure experiments. In order to do so, you must check this box and input an opening angle and an orientation vector of your diamond anvil cell. Perfect simulated data can sometimes be a bit boring. Therefore, we can apply features to our simulation. Most interesting for teaching is the simulation of twins. You can apply any twin law, so it is possible to simulate any kind of merohedral, non-merohedral, or pseudo-merohedral twin. In this case, I would like to simulate a non-merohedral twin and apply a twin law angle of 2 degrees. It is possible to override the instrument model. So the data will be collected with an offset instrument model, and during data processing, it will be necessary to refine the instrument model. Furthermore, you can simulate crystal jumping and sudden orientation changes. The intensity modulation will modulate the intensity based on a given frequency of frames. Both of these features will need to be addressed during the integration of the data. We can even simulate a background. Of course, our detectors are noise-free, but background from air scattering is still visible. Therefore, let's add some background for more realistic data. I choose a nice high scale factor of 5. Generator tripping will cause the generator to ramp up again, while in reality, this happens extremely seldom with our current sources. The software knows how to handle it. The simulation of powder data is again a very interesting possibility and can be used for the simulation of powder experiments. Of course, you need to choose whether you want to simulate a twin or a powder. If you wondered how to do a powder experiment with your single crystal instrument, you should see my last webinar on YouTube, which has been concerned with that topic. So after having addressed all options of the simulator, I click OK. I close the command shell. And I start a new experiment by clicking the Start Stop button and start new. I now screen the sample. Please observe this nice high background. Oh, and already from the first frames, you can see some a little bit too close reflections. So after this is finished, let's start a pre-experiment to better assess the crystal quality and these features. And in order to do so, I open one of my favorite tools in CrysAlis Pro, which is the Ewald 3D. So Ewald 3D gives a live reciprocal representation of the detected intensities. And already from these first first frames, you can easily see that there's something wrong with the crystal. You can see this nicely twinned structure. I'm going to stop the experiment here. So some lucky student might be happy to solve this twin. And CrysAlis Pro is of course the best tool to do so. However, that would vastly exceed the scope of this webinar. If you're wondering how to solve twins in CrysAlis Pro, there is a webinar on the treatment of twins already published, and another webinar on the separation of multiple diffraction patterns is coming up very soon. And with that, I would like to return to my slides. Okay, so after we went through the options and possibility of the simulator, let's talk about some ideas how you can apply this in teaching. The simulator can be a great tool for training designated instrument users without blocking the instrument or without having one. They can train the general diffractometer usage and data collection workflow. Then they can acquire new skills in CrysAlis Pro, like the collection of powder data or the design of custom data collection strategies. Also, for the students of your crystallography lecture, the simulator can be a valuable asset. In any lecture hall or even remotely, you can give a live demonstration how a data collection looks like. You can produce data with clear-cut simulated problems to teach how to address twinning, wobbling, or other experimental problems. Last but not least, you can simulate data from made-up structures and give them to students to process them, maybe as an exam, without having to worry about them using the database. All of this is only possible due to the great CrysAlis Pro software. I myself started using the program only half a year ago, and I like it very much, especially because of such clever features as the simulator. The software is truly user-inspired, and our great team of programmers is well accessible to all our customers. You can meet them on conferences or just send them an email. They are also very active, and there's an update almost every other week. The software is very versatile and comprises all tools for successful data processing within one software. Especially when compared to the other options, CrysAlis Pro runs extremely quick and smoothly. The software does not require licensing and is accessible free of charge to all of our customers. So please register to the forum, get the latest version of CrysAlis Pro, and of course, run the simulator. And with that, I would like to thank you all very much for listening. I hope you enjoyed this webinar. Please stay safe and healthy during this time. We welcome your questions and suggestions for future webinar topics. If you have another suggestion on how to use the simulator, please share it. And once you employed the simulator in teaching, we would be glad to get your feedback on how it went.